Thank you. How's this? Oh, it works. Good morning. Before I start, because we have a couple minutes, I think I want to take a picture because this is the first time in years that I see a three-dimensional audience. So I'll do one like this because it's like high res, and then I'll do one like this. Awesome. Great. Good morning. Thanks for coming up the Gurte. So I get to go first. My name is Pim van Pelt. I am Dutch. I speak English because I grew up in California. I've been active on the internet for a while, since the mid-90s. Let's say 97 was the first RIPE meeting I went to. Active in the SwiNOG community, not always equally active since about 2007. That's because I moved here in 2006. I'm reachable as pim at ipng.nl. I have a RIPE handle too, of course. And as well at pim at ipng.ch. Obligatory, you must register your vanity domain as soon as you move into a new country. And I incorporated IPng in 2021 because I got like really bored during the pandemic. So I live at sea, a tiny little town in Zurich, Brüttizellen. It's known only because it has Brüttizeller Grütz, where we always have our traffic jams every day. I am a tiny operator there. I run this network between D and E, which if you're local in Zurich, it's Interaction and Entity in Rümlang. And as well the Zurich city itself. And because I have some friends, I also operate the European ring with 12 routers, and they run Bird. And so if you're a silicon vendor, you like your Junipers and your Ciscos, you may think, why would you run Bird on a respectable 10 gig European ring? And that's what this talk is about. So I appear on the flap, except that for me, the L is not London, it's Lille. Small difference. Frankfurt, Lille, Amsterdam, Paris. And about 1,850 adjacencies. And I started off with an AS number that you get when you become an LIR at RIPE. But I also had in the corner a dusty 4-digit AS number, which I acquired from an old project, 6-Axis, which you may have heard of, an IPv6 tunnel broker from back in the day. And I renumbered my network while it was running VPP and Bird into AS8298s. So, Linux, Tux here, as well as his friends Beastie and Puffy, do packet forwarding in a very clumsy way. Typically, it's doing a thing, like it's rendering your cat video on YouTube. A packet comes in, and it has to stop what it's doing, look up the content of the packet. There's a huge decision tree on the left. Is this ARP? Let me answer the ARP request, right? Is this an IPv4 packet? If so, like, was it for me or was it for someone else? Should I be handing it off to the local TCP stack or should I be forwarding it? And if so, where do I forward it to? Enfin, like you know this thing, right? So this 9-step plan is essentially read the packet, do something with the packet, and then marshal the packet back for transmit on another Ethernet interface, and then like render your cat video again. So if you have a lot of packets, this is actually not very efficient at all. You don't notice this because you have a very fast CPU. But your CPU cache hates you because it is, in fact, very slow. So what if you didn't do it in that way, where you get an interrupt and then handle the packet, sort of forward the packet, but instead stop using the kernel at all? Now this is counterintuitive, at least it was to me in the beginning, because the kernel is like ultimately the awesome place to be. But the kernel stack is very inefficient because it's very general purpose. If you become very bespoke and very specific in what you want to do, you can become much more efficient, which I'll show at the end of this talk. So there is a library that Intel wrote called DPDK, the Data Plane Development Kit. And it's user space. It asks the kernel for access to the network device. So you no longer have the kernel driver. You don't see ETH0, right? You see nothing. But instead, you can have a user space process that binds the network card and starts interacting with it. It uses all these fancy technologies like SRIOV, user space I/O, virtual functions, like all that stuff. And then it typically fully consumes a CPU, right? So you would run this, and the CPU load goes to 1. because the thing is continuously pulling the network card, asking it, do you have anything for me to do? Which is called a pull mode driver in the lingo of DPDK. So these PMDs are often written by the network card vendors like Mellanox and Intel. They have these things. And if the hardware supports any offload capabilities like checksumming or VXLAN or all that type of stuff, it'll help you out with that in the silicon, but otherwise just hand you these packets with a little descriptor that discusses the packet itself. And then further, what if we had things like a ring buffer lockless so that we can have as many threads as we want, not wait on one another and block on one another. Buffers, hash tables, timers, like all that stuff. So these DPDK threads that are shown here at the top, these L cores, they essentially ask the PMD, give me work. And if you had only one core, it would get all the work. But most vendors for network cards allow what is called RSS, receive side scaling, which hashes the inbound traffic and emits them to multiple threads. So these are depicted here by these red lines. You can have 1, 2, or as many as you have CPUs, really. And that would linearly scale the amount of processing each one of these cores could do. And then on the way back out, every one of these threads might have a transmit queue to each one of the network cards. So if it has something to say, it would just marshal a packet out on its TX queue, which would make the hardware sort of send a packet. So far, so good. A program like that roughly looks like this. You initialize something called an EAL, the environment abstraction layer, which takes care of all the nitty-gritty stuff like figuring out the PCI and like the memory and the huge pages and like all of this stuff. And then eventually, it is as simple as writing a loop, an infinite loop, that loops over this red function, the Ethernet RX burst function, and does something with the result. And then the green function, which is the Ethernet TX burst. And one thing to note here is there is packets plural. This is not one packet that we might be asking the kernel to give us, but a whole list of them, say 32 or 256. And so if there are these packets that are already in the network card's memory, we would just ask for all of them in one go. Now you may be thinking, why does that help? It helps because memory is really slow. Like we're always told memory is super fast because like hard drives or network cards, but actually memory is super, super slow. And if you think about it, like this table here, your CPU has a little bit of memory as well. Depicted in the middle here, it's about a third of the chip size is just local memory, and it's called L1, L2, and L3 cache. Typically, the L3 cache that I have in the bubble here is shared by a number of cores, and then the L2 cache is specific to a CPU core, and the L1 is very close to where the registers are, and it's super, super fast memory. So to think about the differences there, a half a nanosecond is how fast the CPU can be reading from local L1 cache. 3.5 nanos today for like an i7 CPU, normal Intel CPU. For the L2 cache, 10 nanoseconds for the L3 cache, and like 7 times slower to read from RAM. So the clue here is don't read from RAM. And certainly don't read from RAM across a NUMA domain if you have multiprocessing, because that's even slower. That's like 200 milliseconds. We're talking a 400x difference in speed between L1 cache and memory, which we were always taught is fast. So remember I said read 32 packets. The linear scaling that we do, the linear processing that we do in the Linux kernel and the FreeBSD kernel and such, they read a function like L3 input or a lookup or checksumming, and then do that for each individual packet, which means the next one has to go read all of that stuff again. And the chances that this stuff is in the CPU cache is actually quite low. So we can actually optimize and flip the entire thing around and say, let's actually do Ethernet input for all 32 packets that we just read. Because the first packet will not hit a warm CPU cache and load whatever instructions it needs to do that function, Ethernet input. But then the second through 32nd packet goes super fast because we don't have to touch the memory at all. The packet is already in the data cache of the CPU. The instructions are already in the iCache. And so that means you have a 20, 50, 100 times increase in throughput if you have more than one packet to handle. So in this thing called vector packet processing, VPP, you do this on lists of packets. So they all go through this directed graph, figure out, is it ARP, is it IPv4, is it IPv6, or MPLS, whatnot, and then branch off. Sort of parts of these packets go different directions through the graph, but ultimately they all get processed much, much, much quicker. Specifically because modern CPUs can do the same operation on multiple data points, called SIMD, SSE, or AVX are two common ones, and it allows you to do things like add 1 to these 900 things, and it takes you 1 clock cycle, or maybe 2, which is different to add one thing 900 times, which would be 900 clock cycles. And it's significantly faster to do it this way. And because we're running this as CPU threads that are consuming the entire CPU, there will be no competition, no thrashing, no context switching, no memory TLB misses, so you always have what you need very close with you. It's really, really fast. So, as I said, you don't see an ETH0 anymore. When you start VPP, it runs as a process. You can see it take 100% CPU or 600% CPU if you had 6 CPUs on it. And then there's a command line tool called VPPCTL. And with that thing, you can type what I typed here in this window, set an interface to up, set the MTU to 9000, give it some addresses, give it some routes, and then start forwarding traffic. And you never see the traffic. There's nothing to TCP dump. There's no interface anymore in Linux, right? The process is all in user space. But it's going to be a little bit faster. This is a screenshot from a machine called Hippo. Hippo is my development machine. If you ever heard of Hungry Hungry Hippos, it was a game back in the States where I grew up. And so Hippo is always hungry for packets. But as I said, you don't see ETH0 anymore. And VPP is a data plane. So it's really good at forwarding things. And the community at VPP did not want to build fully fledged routers out of this, with BGP and all of that stuff. But they do allow to write plugins. So I contributed a plugin that essentially creates a TUNTAP interface in the Linux kernel. This is a virtual interface, and you can give it any name you'd like say ETH0, right? And it's user space connected, so any traffic that goes in or out of this interface goes into this process, which happens to be the data plane. So what if we now make a mirror of this 10 gig Ethernet interface that I configured before and make it appear in the Linux kernel as ETH0 again? And every time Linux wants to send a packet into this interface, I read it in VPP and I know what to do with it. It's a packet. I can just schedule it and make it emit, go through the routing table, just like any other input, really. And if VPP gets traffic that goes through the data plane, it just forwards it as per normal. But if it goes to the IP address that I configured on the data plane, then it's like, aha, this one is destined for me, so I can just send it into this tap. And so at this point, Linux would see on ETH0 all the traffic that goes to my IP addresses, and it would see nothing that goes through the data plane. That's cool. So now I can maybe send it traffic and do some pings. But typically, at least in Linux, there is a heavy use of netlink, and netlink will allow us to send messages between user space processes in the kernel to do things like set a new interface, set a route, set an IP address, change the MTU, like all of that type of stuff. If you were to listen to those messages in VPP, you could see an operator do all sorts of stuff with that interface you just created. You know, like IP or routes or like all of the above. So now this talk could have been about the implementation itself, which was about 30,000 lines of code. And I'm not going to do that because I only have half an hour. But if you are very curious, it is a 7-part expose that I documented in a bunch of articles around the things that make this work. In particular, be able to create interfaces in Linux. That's the first one. It's table stakes. And then the second one is sync state changes, MTU, IP addresses, and all that stuff that you apply in VPP to the Linux side. And then the third was kind of a gimme. Automatically create sub-interfaces. So if I have a VLAN device that I create, plumb it as well through to Linux. And then part 4 would be the other direction. If you had an interface in Linux and you changed it, you created an IP address or a route over it, copy that back into VPP and apply it to the data plane. Part 5, that's the hardest one. By far, that's routes. If you want to set like a BGP full table into the forwarding database, you need to handle it with care. So there's some more code written there. And then, as I mentioned earlier, you can't see any traffic that goes through the data plane with normal Linux tools like TCP dump. And so certainly things like interface counters would only count the stuff that VPP sends to the machine, but not the stuff that it's forwarding. And so I had to write an SNMP plugin, right, to expose all of this stuff. And then finally, for those crazy enough to try it, a little how-to on how to install and configure one of these. The difference between the first screenshot and this one is here, I only type one command, which is VPPCTL Linux control plane create that interface into a host interface called XE0. And from that point on, that interface exists in Linux, and I can do anything I'd like with it. Create a VLAN, create a name, set a route, set a default, ping Google, it just works. Right? So at this point, it looks like Linux again, which is really nice. But if it looks like Linux, I can probably also run Bird on it. Turns out I can. I can run Bird, which does full BGP, multiple tables, OSPF, IPv6, multicast, all of that stuff. The difference is it does it a lot faster than commercial hardware does. So full tables will fully converge into the fib in about 9 seconds, which is really cool. And I mentioned earlier, like, you only see traffic that goes to the machine, not through the machine. So you need to ask VPP, you know, what are your interface stats, what are you forwarding, and all that type of stuff, and then add that to the traffic that you had on the actual ETH0, which is a very simple SNMP agent that I published on GitHub that allow you to add the thing to things like LibreNMS or other open source monitoring tools. I use Libre myself. The little doggy logo was one Git pull request, and the other one was to make VPP make LibreNMS aware of VPP as you run it, so that it knows how to render the doggy when you have a machine like that. Casually forwarding 18 gigs of traffic, this machine. And it's not even breaking a sweat, which we will see later. But I was speaking about DPDK, and Yoda would say there is another super useful DPDK app. And it's made by Cisco. It's open source as well. It's called T-Rex. It's a traffic load tester. So essentially it generates synthetic load, and it replays things like HTTP, stateful traffic, against a device under test, a DUT. And it has a Python API, so you can program it up the wazoo and tell it to ramp up and down and do more traffic, different types of traffic, all that stuff. And it's also a DPDK app, and it's pretty fast. It does about 15 million packets per second per core that you assign to this app. So if you had a 32-core machine, you would probably bump 200, 250 million packets per second, which is nice. And because DPDK itself supports all sorts of network cards, you know, Intel, Mellanox, and that stuff, you can arm it with a 40 gig card or a 100 gig card and just do line rate 64-byte packets with a commodity $2,000 machine. So we don't need XCI anymore. So it kind of looks like this. So the TRX machine has, in this case, 2 network cards. It could have way more, but for simplicity. And it has a little configuration YAML file that says, here's your PCI address. These are 2 10 gig cards in this case. And you can give them MAC addresses and then tell port 1, source from this MAC, the purple one, and send it to MAC B, right? And that will send it to the other port. And then port 2 is like sourcing from MAC B and then sending to MAC A again. So essentially, if you have a loopback connection between these 2 ports and you send a bunch of traffic, you'll just see all the traffic emitted on one port and then back into the other, yes? And T-Rex works such that when it emits a packet, it expects it back on the other interface. And if it stops seeing those packets, then you know they're being lost somewhere, right? Typically in the device under test. So you start T-Rex like this, and then you have a little console, which I'll show a screenshot for. And if you don't want to use MAC addresses, you can as well just type IP addresses, and the thing will ARP and resolve who is 100.65.1.2 and send traffic to 1.1, and then on the other port expect it back. So here you can actually test a DUT as an L3 system, or indeed an entire network that is just forwarding, provided the traffic that you inject in the purple side emits back on the other side, so T-Rex can see if the traffic is being forwarded or not. And then with these stateless traffic profiles, they use an open source library called Scapy, and it's essentially a way for you to generate arbitrary packets in Python, and then replay those packets at a certain mixture ratio. In this case, there is a a well-known traffic mix called the internet mix, IMix, and it's like a ratio of a bunch of small packets, medium packets, and large packets. And then you apply such a thing on a port, and then you tell the port, please send at a certain rate, like 1,000 packets per second, or like 10% of line rate, and it will do that, and then expect the packets back on the other side. So to do this load test, I have two methods to figure out how fast a machine actually is. Method number one is take VPP and give it one CPU. That's all it gets. And then just load up the port as fast as it will go and count the amount of packets that you see on the other side. Then you know this one CPU core can forward approximately that many packets. And then method number two is a little bit more advanced. It essentially starts very low and then starts ramping up traffic from like 0 to 100% of the line rate, say 10 gigs or 100 gigs if you had that network card. In a number of minutes, like maybe 10 minutes or so, and then keeps it there for half a minute, and then stops the load test, and you're trying to find the point at which the device under test stops forwarding. So the first method is very straightforward. In this T-Rex console that was a couple of slides ago, you can type these commands, like start this profile on port 0 with 1,000 packets per second. You can pause the traffic, you can resume the traffic, you can update the profile to be 1 million packets per second. By the way, little nit, I typed a capital M here. That's actually a syntax error in T-Rex because they're morons and they do millipackets per second. So you actually have to type small m, but I couldn't bear to have a slide that said a small m and get yelled at. And then you can update it to say 10 million packets per second, which would be almost line rate, about 2/3 of it. Or then just say update -m 100%, like fill the line. And it gives you a little textual user interface. I like that. It doesn't have to be graphical for me. And the anatomy of it really is like number one there, the ports that you have. You can have any number of port pairs. I had two 10 gig ports here. And then at number two, you can see the traffic that we're emitting on these ports. In this case, it's 19.1 gigabits of layer 1, actual bits on the wire, and about 18 gigs of L2. And then, of course, we're expecting this traffic back, so you can see at number 3, how much are we reading of the stuff that we wrote? And you would like that to be the same number, which it is in this particular case. And then if you want like all the stats and all the numbers, there's a bunch of counters under that with number 4. This load test here is doing an IMix bidirectional load test where both ports are sending 3 million packets per second and expecting them back on the other port. Right? So you would do about 19 gigabits of duplex traffic. For the second one, I had to write some code. So there is this T-Rex load test.py, which you give a bunch of command line arguments, and then it runs that profile. Remember that I was talking about. And then for the profiles, and this is something not everyone knows, you could do this really easy, and a lot of vendors will say, like, we do up to. Every time someone says up to 40 gigabits, they're fibbing, because they're taking it easy. They're sending, like, really big packets. People often say, like, I did an iPerf test. Like, that's meaningless, which we'll see in a little bit. Because it's only 800,000 packets per second to saturate a 10 gig line. This IMix that I spoke of earlier, that's representative traffic. That's what you might see in a residential network. About 3 million packets per second at 10 gigs. And then you can also send 64-byte packets, like the really small ones that you often see in a DDoS, which would be 14.88 million packets per second, a number that many of us may recall. And if you send this from multiple sources and addresses, we can use multiple CPUs to handle this traffic. And then the fourth one, that's the insidious one, is to just replay the exact same packet over and over again. And you would think that this is more efficient, but actually often not, because it means that the CPU is restricted to only use one thread, which means even if I had 32, I'm only going to use one of them. So I take 3 machines, a small one that's $650, a medium one from Supermicro, and a big one, which is Hippo. And if I do this and I count the amount of cycles that my CPU needs to switch one packet, and I'm doing about 1,000 packets per second, it turns out the Atom will take about 4,900 CPU cycles to forward one packet. The Xeon, which is that Supermicro, will take 2,000, and the Ryzen would take 1,100 or so. But if you load it up, and go from 1K to 1 million packets per second, the vector size that I mentioned earlier grows, and the efficiency goes greatly up. So now all of a sudden, the atom is taking only 620 cycles per switched packet. And at 10 million PPS, it's taking 350 cycles. And that's where it sort of stops. So it doesn't do 10 million. But it does end up doing 5 million packets per core, which is really, really great. The Xeon doubles that. It's a more efficient CPU type. And the Ryzen, it's just a completely crazy architecture with 32 cores, or like 16 cores and 16 hyperthreads. And the threads are super efficient. So it does 22 million packets per second on one CPU. So method 2, that's that ramp up that I was describing earlier. It starts off for like half a minute just warming up to make sure everything works. You see the traffic at all, right? Because sometimes you misconfigured things. Then it might ramp up to 100%. And when it's at 100%, it'll hold there for 30 seconds and expect the traffic still to stay at 100% of what it sent. Some devices will only handle a fraction, so a graph will look like this. It goes up with load, and then when the load hits a certain sort of maximum saturation point for the device, it'll flatline. And other ones can just handle the entire line rate, so they go up with the inbound traffic, send you all the traffic back that you sent it, and handle 100% of line rate. So as a baseline, Tux and Beastie are terrible. So they're actually down there. All of them are maybe 100,000, 500,000, but less than 1 million packets per second. Even on the really big CPU. Turns out the Ryzen does about 880,000 packets per second. That's not a lot. So let's start with the simple test, the one that vendors will say, we did an iPerf test. Well, everyone can win. The line looks weird, but that's because everyone tracked to 100%. Right, so it doesn't matter. But again, this is only 800,000 packets per second. And we can still all be a winner if we do IMIX. So this is 3.2 million packets per second. And we already saw that the small CPU can do 5 million, right? So it's unsurprising. And even in two directions, it's unsurprising because you can use two CPUs, one on the one direction, one on the other direction, and each can do 5 million, right? So you can expect this to be just fine. So we're still good. It gets a little bit more dicey when you do line rate. So this is this Atom CPU, the Atom 3558. And one CPU thread will do that 5 million QPS, or packets per second that I showed. That's the blue line. The orange line is when you add another CPU to it, and it'll do about 10 million. And then the third line will do about 15 million, which is more than what we need for 14.88. So you can see this Atom will do line rate in one direction with 3 CPUs, which is kind of nice because it runs only 16 watts of power. It's very cheap. So the Xeon is a bunch faster, so with 1 queue it does 10 million, and with 2 queues, of course, it aces the test. And the Ryzen doesn't care, because it does 22 million packets per second per core, so if you have 1 core, it's more than the needed 14.8, so it's like whatever. So if you do a single flow, though, it gets different, right? Remember, the single flow always hashes to the same CPU, and you can totally see the Atom there, no matter how many queues you add, how many CPUs you might add, they're all going to suck at 5 million packets per second. I say suck lightly. It's actually a lot of packets. The Xeon does 10. You can see all 3 threads will bottleneck at 10. Doesn't matter if you added even more threads. And then the Ryzen, because it could already do it with 1 CPU, obviously it can also do it with 2 and more. So the last thing I wanted to say about it is, like, raw forwarding isn't everything. The netgate is cheap, like monetarily, but also power-wise, right? So I did this math. I thought it was funny. How many microjoules does it take, or joules does it take to switch 1 packet? Turns out 1.24. The Supermicro has a little bit more CPU. The Xeon is better than the Atom. It also has hyperthreading, and you can turn on hyperthreading. It reduces the throughput per core from 10 million to 6 million, but you have more cores. Right? So instead of 4 times 10, you would have 6.3 times 8, which is better. But even at 3 threads, it takes about 48 watts, which is 1.5 microjoules per switched packet. The ASRock, it's a bigger machine, right? It runs 265 watts. And if you were to fully load it, which I can't do yet because I am looking for a load tester that will do much more traffic, at 15 threads, it'll do about 300 million packets per second. So that's 0.8 joules per packet, or microjoules per packet. but it will be constrained by PCI bandwidth. Like, because it only has 24 lanes of PCI v4, whatever, and it's 600, 700 gigabits of max throughput. But the machine costs 2,500 francs. So for 2,500 francs, you can easily do multiple 100 gig links in both directions. And that's what I wanted to say. So thanks for your attention. If you peer with IPng, thank you very much. It's very useful for this code that I wrote to test in a live scenario. If you don't, please do. This is a thinly veiled peering request after all. And I have some resources on where you might read up and follow the latest in live. Thank you for your attention.
Thank you very much. Yeah, you're on time. Are there any questions?
So you talked a lot about DPDK. You have any experience with XDP framework?
A little bit. So VPP is often assumed only to work with DPDK because that's where it started, but it has an XDP driver as well. It also has AVF drivers, like all sorts of stuff that's not DPDK based. I have some limited experience with it, but I'm not a huge fan of programming the kernel with like direct line little micro programs that aren't Turing complete for obvious reasons. And so for me, I never considered XDP as an alternative. I like the full processing capabilities that I might have in user space.
Okay, it's just because the XDP is from the Linux kernel developers part. So. The other question is your framework, which you said with the nice plugin with the netlinks and stuff there. Does that only work for TCP traffic, or you have any experience with like doing multicast or something on that framework?
Yeah, it does. It does all L3, IPv4, and IPv6 traffic types. So it will do multicast, unicast, v4, and v6. And other protocols could be added. It can be a little bit fickle sometimes. Things like MAC VLANs, you know, what you might find for VRRP, are implementable, but I haven't implemented them yet. So, but it does do all multicast and unicast.
Thank you. Any more questions? Okay, so thanks again, Pim.
You're welcome.